Um, Bill's a senior geologist and project manager with Aptum Federal Services LLC and has over 30 years of experience in environmental site investigation and remediation throughout the continental U.S. He's currently responsible for managing diverse technical teams in the investigation and remediation of contaminated Department of Defense and former commercial waste disposal sites in Texas, New Jersey, and Mississippi. He grew up in Friendswood, southeast of Houston, as the son of a mining geologist and spent his summer vacations as a kid visiting mining exploration sites throughout North America. He claims he was around 10 years old when he realized that not everyone spent their summers learning about geology, which I love because my kids had the same issue because both their parents were geologists. So I think it's great. And he's going to give us a presentation about Texas geology and things we need to know about. And then at the end, his second part is case studies, and those are my absolute favorite part. So be sure to stay tuned.
Okay. Thank you very much for the intro. Let me get this spooled up and just for y'all, are y'all seeing that okay?
Yes, we're seeing it.
Okay, good deal. So as she said, I grew up as the son of a geologist, and I like the joke that I spent all that time learning geology, and then my dad spent my late high school years trying to talk me out of being a geology major in college. He always said it made a great hobby. Um, but I followed in his footsteps to some degree. He was a mining geologist, and I went environmental coming out of college. And all my college professors in the early '90s tried very hard to convince me to go oil and gas instead because environmental was just a fad and it was going to be gone in 5 years. So I feel quite fortunate to have survived the fad of 5 years and be 30 years later still working on the same types of projects and watching the field advance in ways that they could have never imagined back then. So, going to talk to you. I helped develop this chapter long, long ago in a galaxy far away with Dr. Chris Mathewson, who was a geology professor at A&M at the time. And we put this together, and I think it's been updated several times since then by other folks. But there's a whole lot of material covered in this unit. And what I really want to do is kind of boil it down, not to the real hard nitty gritty details of geology itself, but how did geology interact and how did it help form the geology of Texas? And then how does that affect the things that are around us and the things that make up the rest of the ecosystem? So I'll just clarify here, there's several parts of this where I'm boiling down, an entire semester long class into about 2 slides. So there's going to be, for everything I state is unequivocally the case, there's going to be cases where that's not the case. So if you're a geologist or if you've had multiple geology classes and you're sitting there thinking, well, there's a case where that doesn't apply. Yeah, I agree. But we're really trying to cover broad topics and really try to just boil it down to how, if as somebody who's not a geologist walking around and learning about ecology and learning about the environment around us, how does the geology affect what we see and what we experience? So that's my goal for going through this unit tonight. And as was said previously, I'm going to kind of go through the basics of geology in Texas for an hour, and then we'll take a short break and then go into some case studies of, okay, how does the geology affect us, or how are we affecting the geology and the geomorphology around us? So I think that's the more interesting part of this. So bear with me as we try to get through the first part, because I think it's necessary to be able to understand the parts that we talk about later in the case studies. So these are the unit goals, kind of talk about all of these things. I'm going to go through, the geology history and some slides of where Texas was through time in relation to the poles of the globe and what was happening around us. And then the landform regions, I'm going to show you the landform regions. I'm not going to go into each of them and talk about them, but I am going to talk about how they relate to the ecological regions and other features that we see. And then the hydrogeologic cycle, I'm going to talk a little bit about that, but not real deeply, but I will talk about how it kind of affects us all. And then for soil, I'm not a soil scientist. I had one soil class in college, one soil science class, so I know just enough to be dangerous. But they want to talk about all the physical and chemical properties. I think the chapter in the unit for soil does a good job of describing that for you. So my goal for this is for you to understand the difference between what is geology and what is a geologist looking at, and what is soil and what are soil scientists looking at, and how to find out more information about both of those and understand the difference. So boiling down geologic processes, this is, kind of a story of the big picture and then the little picture. So if you look in the dictionary of geology, it talks about the scientific study, the origin, history, and structure of the earth. So we're going to spend about 3 slides on that big topic. But the big picture of that is, and I'll show this graphically in a moment, there's really 3 parts to the earth that we know about. And everything that we know is limited to the crust down there at the bottom. So we've got a core in the center of the earth that is uh, liquid, but probably has a solid metal center. We don't know that for sure, but what we know about it from geophysical sensing suggests that we have a solid metal center to the core, probably nickel, iron, and a lot of other really heavy elements, probably some we don't even know about. And then there's a mantle that's in between that and the outer crust of the earth. And that mantle is partially melted, kind of viscous material. It's not solid, it's not liquid, but it's somewhere in between. And then we have this thin crust. And when I say thin, we're talking a few miles, deep relative to several thousand miles of to the center of the earth. So what I like to describe this as is, if you think about eating a bowl of chili con queso at a Mexican restaurant, when they first bring it out, it's all liquid, right? But as soon as it starts to cool off, you get that really thin skin of uh, cheese at the top that kind of gets a little more solid, a little more pliable than the liquid cheese underneath it. That's kind of what we're sitting on. We're the crust. We're this very thin skin riding around on top of the mantle, and it really is, a fairly good analogy for what we experience here. So this is one of those slides where I'm going to boil down an entire class on plate tectonics into about 2 slides here. So bear with me. Um, so when we talk about plate tectonics, the plates are just pieces of that skin I was just talking about. They're pieces of that crust that's sitting on top of the semi-molten mantle, and they're riding around in response to heat and other changes that are happening underneath them. Where we have upwellings of magma or molten rock from the mantle through the crust, it can fracture the plates and basically push them around, move them away from where the magma is upwelling. And that's what generates the movement of plate tectonics, is that upwelling of magma from the mantle. And it also, as it's doing that, it creates new crust, and that new crust needs space to be. And so it's pushing the other pieces away and moving them to other areas. And in some cases where they collide, one will go underneath the other, and it's destroying the crust in those areas and pushing it back down into the mantle. We'll look at all this graphically in just a minute, but so you'll hear us talk about a couple different kinds of plates. There's oceanic plates, and if you think about when magma erupts at the surface, there's really 3 things that can happen to it. You hear people talk about igneous rocks, and there's intrusive igneous and extrusive igneous. You don't need to deal with all of that to understand that basically when magma or when lava comes out at the surface of the earth, the speed at which it cools controls to some degree how it controls absolutely how fast and how large the crystals form in the rock, but also it has an effect on how dense that crust is. So where magma is coming up underwater at a mid-ocean rift, it's going to cool very rapidly. There's not time for air or other things to get entrained into it. And so that magma crystallizes into very dense material that, when it forms these oceanic plates being pushed away from the upwelling areas, it's very dense, it's very heavy, and it's going to try to stay, it wants to sink when it collides with other plates, essentially. When you have continental plates, these are plates that are made up of older and lighter material where you've had maybe multiple uh, collisions of various plates. You kind of scrape the tops off of some of the material. You have uh, land-based eruptions of volcanoes and things like this that have piled up material much thicker but also lighter. So oceanic plates are generally going to be, maybe 10 kilometers thick. Continental plates may be 50 kilometers thick, just depending on how old the continent is and how much of the material has been moved around and how many collisions have occurred. That's going to determine how thick the plate is. But the continental plates are generally lighter and the oceanic plates are denser and heavier. And so when they collide, the oceanic plates are always going to go underneath the continental plate. So this is kind of a graphical representation of what we just talked about. There's the inner core down here. Can you guys see my cursor when I'm moving my cursor around? I'm not seeing it now. I don't know what's going on here. Okay.
Yes, we can see
Anyway.
it.
Okay,
We
good.
It's it.
I kind of know where it's moving here, but anyway, so there's this inner core, outer core that's a liquid core, the inner core is solid. And really what's happening in the mantle is it's a giant heat engine. Basically, there is radioactive decay and other heat generating processes going on in the core, and that heat needs to get out and wants to rise up to the crust of the earth. And so the most efficient and effective way to do that is by transport through the mantle. So not just radiative heating, but also movement of semi-molten, semi-liquid uh, rock upward. And as that reaches the surface, it's going to erupt here up here at the ridges, but it's also going to generate kind of these circulation cells, where as it reaches the surface and cools off in contact with the crust, it'll start sinking back in as it cools. It's just like the atmosphere where we have warm air rising and cold air sinking. It's the same thing going on in the mantle where you've got warm material, heat rising, cooled material, and crustal plates wanting to sink. And what that does is creates this, like it says up here at the left, the slab pull. It's basically pulling these slabs of the crust around and moving them laterally across the surface of the planet. And that happens over thousands and thousands of millions of years, but it's the motion that is responsible for all of the topography and all of the geomorphology that we have on the planet. If we just had, static plates and we had these eruptions, you might have, a volcano, but without the movement of the plates, you wouldn't get a lot of the topography we see. And I'll give you some examples of that here in a little bit. So when these plates move against each other and collide, we have what we call tectonic boundaries or plate boundaries. And there's multiple types. There's divergent boundaries. You've heard me talk already about a rift, and these are areas where magma is rising up from the mantle. The crust is separating and the plates at that location are moving in opposite directions away from each other. And so when you hear people talk about the Mid-Atlantic Rift or the Pacific Rise, things like this, these various rift uh, type situations, or even the East African Rift Valley, these are all places where plates are moving away from each other and magma is moving to the surface and causing that. There's convergent boundaries, and I've got it labeled subduction here, but there's multiple types of convergent boundaries we'll talk about in a little bit. But convergent boundaries are just where two plates are moving towards each other and where they're colliding. And as I mentioned before, if you get an oceanic plate intersecting with a continental plate, the oceanic plate is always going to dive underneath it. If you get two oceanic plates converging, they will usually, one will dive underneath the other. They don't usually do a collision. But when you have two continental plates that collide, um, it gets really messy. And I'll kind of show you an example of that when we go through kind of the slides of the history of where things have been on the planet, and talk about what that does to the situation when that happens. And then the last is transform boundaries, where you have one plate moving past another plate laterally, but not colliding and not diverging. And this is usually in cases where you're along an offset portion of a rift, or in your areas where you have a rift and multiple plates around it. You can get one plate moving past another laterally. And then the most famous version everybody probably knows of this is the San Andreas Fault. So the basically, everybody talks about whether California is going to fall into the ocean, and that's not going to happen. But Los Angeles is slowly moving towards San Francisco and vice versa, and one will eventually be a suburb of the other. But they are. This is a transform boundary between two areas where a rift is spreading, and that you have one plate moving to the north and west and one plate moving to the south and east in that location relative to each other.
Hey, Bill, we have a question.
Sure.
Is there an element that's predominant in the oceanic plates and the continental plates?
Is there a what?
An element?
Well, the rock type is basalt typically. I mean, it's usually depends on what is being brought up, but it's basically mantle derived basalts typically are what gets erupted there, and it's going to be iron rich and other mineral, heavy mineral rich generally, but um, not one specific element that really dominates in that regard. Um, so this graphic kind of just shows what I just talked about, and this is kind of the intro to, okay, how does plate tectonics affect and generate the landforms we see. So if you look over to the right hand side of this drawing, you see a continental rift zone. And the best example of this that I can give you to think about is the East African Rift, where there's a area where the continent is starting to spread, where a portion of East Africa is moving to the east and the rest of Africa is moving to the west relatively. And that valley is opening up. And eventually, if that keeps going, it will generate a rift and the continents will separate and there will become an ocean spreading center there. If you move to the left into the center of this, you see an ocean spreading center, very similar to what we have out off the coast of Washington, where the Juan de Fuca plate and the Pacific plate are moving apart. Same in the Atlantic, where you have the Mid-Atlantic Ridge going up towards uh, Iceland, in that area where you have basically two portions of ocean spreading apart, pushing continents away from each other. And then along in the middle of the right hand side here, you can see a subducting plate going underneath. This is an oceanic plate moving underneath continental plate. And what happens in that instance is that there's a lot of minerals, a lot of sediment, a lot of other things that are with that plate that's getting subducted down. And as it gets subducted, it gets exposed to different temperature and pressure conditions than it was exposed to at the bottom of the ocean there. And as it goes through that, a lot of the material that's in there melts, the area above it can be melted by the temperature and pressure changes, and it generates lava and upwelling magma at those locations. And so you get, let me see if I can get this. Okay. I think I'm in the right spot because I'm not seeing the cursor, but what you get is an arc along the shore of the continental plate, or within 100 miles or so of the where this subduction is happening. And a great example of this is the Cascades up in northwest North America, northwest United States. All of those volcanoes, Mount St. Helens, Mount Rainier, Mount Hood, all of these different volcanoes along that range are all generated that by subducting plate that's going underneath the continental plate there. Same thing when you get over to the far left here, if you have an oceanic plate going underneath another oceanic plate, you get a similar set of volcanoes being formed, but they generate what we see as an island arc. So if you look at the Aleutians up in the northern Pacific, or if you look over in Indonesia and in the South Pacific, or the western South Pacific, that whole area is island arcs for different plates that are generated by volcanism caused by the subduction of those things. So this is responsible for a lot of the topography. The one thing that's not shown on here is a continental collision, but I'll show you an example of that here in a little while. The other thing to think about is sometimes you get a mantle hotspot, and that's the middle left here on this image, where you have a hotspot of mantle upwelling that is not necessarily related to an oceanic ridge or to a spreading center of any kind, but you have this constant kind of pipeline of magma coming to the surface. And as the plate that hotspot is, as the plate that's over that hotspot is moving, you see that expressed in the on the surface as a chain of volcanoes. And the best example of this is the Hawaiian Islands. So if you think about where the big island is with the active volcano Kilauea on its southeastern side or eastern side, that whole chain of islands and that plate is moving to the west northwest relative to a mantle hotspot that has been feeding for many millions of years the volcanoes that have formed the Hawaiian Islands. So the islands to the farthest to the north and west are the oldest volcanoes, and the Big Island and specifically Kilauea at the eastern end are the youngest volcanoes. And in fact, there's a seamount offshore of Kilauea that's even younger, and it's currently been erupting over the last few thousand years. And time will tell whether it's going to add on to the edge of the existing Big Island or if it will be the next Hawaiian Island if that volcanism there keeps moving to the east relative to the Big Island right now. But eventually we'll have another Hawaiian Island as that plate continues moving and that mantle hotspot keeps moving to the east relative to where the islands are now. Okay, so that's plate tectonics in a nutshell. Now we're going to talk about kind of the smaller picture. So I just said it a few minutes ago, but tectonic forces, that collision of plates, the magma production, the volcanism, generates all of the topography that we see. It creates all the topographic relief that we see in large scale on the globe. So, you know, whether it's the highest mountain ranges, whether it's the deepest ocean trenches, whether it's, you know, big volcanoes and things like that, that's all related to tectonic movement, tectonic forces causing those things at different scales. And water is the most significant erosional agent by far. So even in the middle of the driest parts of the desert, one rainstorm will move more sand, more rock, more dirt around and reshape that area than all the wind blowing in between the rainstorms. So it does physical movement, but it also enhances chemical weathering that weakens and transforms solid rock into soil. It also helps with fracturing processes. I don't know how many of you guys have been to Enchanted Rock, but if you've been up on top of the rock or up on the sides and you see these giant slabs of rock that are just seem to be kind of hanging there, and that seems like this large solid boulder of granite, right? But when you get down into the you know the microscopic scale, there's fractures in that rock, and you get a little bit of water in there, and that water, when it freezes, expands and pops that fracture open a little more, and the next time it pops it open a little more, and over time, thousands of years, you get enough of a crack that you pop one of those slabs loose. And the Native Americans would used to hear this rock cracking and popping, and some of it was just the heating and cooling at night, but also during the times when there was freezing and ice on the rock, they would hear this popping going on, and that's what made them think that Enchanted Rock was haunted or was occupied by spirits. So the it is a significant factor, significant weathering process, just that microscopic freezing and thawing that goes on in small spaces in rocks like that. So, and then lastly, the other thing that will transform our rocks and our material from what we see today to what it become or what we saw millions of years ago to what we see today is heat and pressure. So we can get, like I mentioned, when you have plate subduction and things like that, and you get volcanism occurring through overlying rocks, you can get heat and pressure that will transform the rocks. And we talk about those as metamorphic rocks. If you're familiar with that phrase, you can see more description of it in the geology chapter. But like around Enchanted Rock, there's a ring of rocks around that. The Town Mountain granite is the main rock that was formed by the magma chamber that became Enchanted Rock as it cooled. And around that, there's a crust of Pack Saddle Schist and Valley Springs Gneiss, which are two different kinds of metamorphic rocks that were formed by the heat and pressure of that magma being placed into where it became Enchanted Rock, where it was all buried underground at the time. And the rocks around it were impacted by that heat and pressure difference and became metamorphic rocks. So those kinds of things are what transforms the rock from what it was into what we see, and what eventually leads to soil and other material developing into what we have down here at the coast. We don't have volcanism, we don't have tectonic boundaries, but the topography and all the processes acting on that topography of what generated the alluvial landforms that we see down at the coast of Texas. Okay, so here's kind of the fun step in all this. So this is like one of those Where's Waldo games. We're going to play Where's Texas and Where's North America as we go through time. So if we start in Precambrian time, this is about 650 million years ago. What we see down towards the south here is what's called Laurentia, or the Laurentian plate. And this is kind of proto North America. This is what becomes North America over time. But you can see this is all done by carbon dating and looking at the magnetic signatures of rocks to know where they were relative to the pole at the time they were formed. And so looking at Precambrian age rocks, we can tell kind of where these things were by the magnetic signatures that the rocks adopt from where the magnetic field of the earth was at the time. So the interesting part about Precambrian time is that everything's upside down, right? Or the opposite of what it is now. So you see the Amazon, you can see West Africa and Florida, Laurentia, Alaska are all basically down at the South Pole. And if you look at Antarctica, it's square at the equator. And it's attached to India and South Africa and Australia. So it gives you kind of a little scope of, okay, things are a little different now than they were back then, right? So what I want you to pay attention to over time is kind of where these things move around and how we develop the landforms as these collisions occur. If you look over on the left-hand side of this, where there's this yellow line with little triangles sticking off of it, that denote when we go through this, that denotes a subduction zone. So basically, the oceanic plate from the left-hand side here is moving towards this mass of continents in the middle, or the mass of plates in the middle, and that's where there's a subduction going on, and you can see along that line there's a series of volcanic islands being formed, and that's kind of how the terrain gets formed into these continents over time as these collisions happen as we go through here. Okay, so Cambrian time. This is about a little over 500 million years ago, the time of the trilobites and things like that starting to come about. This is when we see North America kind of all by itself here in the middle. You can see Laurentia square at the equator. Proto-Mexico is already kind of attached down there. And then the rest of Gondwana land, if you've ever heard the phrase reunite Gondwana land, that's all of these other continents are all kind of stuck together, spanning, almost a full hemisphere here, going around the south end of south side of the sphere. Oh, let me back up. Okay. So Permian time, this is, if you think about the Permian Basin, if you look in the center of the map here, just north of where it says central, that's kind of Texas right now, in 250 some odd million years ago. And you can see it's underwater. It's a shallow basin. near a subduction zone, so there's a lot going on there. But this is when the Permian aged rocks that are form a lot of our uh, West Texas terrains are being formed in this time right now. And then if you look to the south, you see South America, Africa, and Florida essentially are all kind of jammed together. And one of the things that really became the first keys to the idea that plates moved was, as we go to this next slide, and the one after it, you'll see South America and Africa begin to separate. And some of the very earliest geologists were looking at rocks that they saw in Africa and then eventually seeing rocks over in South America and going, man, these look really similar. They look a lot alike, like that stuff I just saw half an ocean ago. And it was that idea of, okay, these continents once being side by side and creating the same rocks in the same place that started the theory of continental drift, which then eventually became plate tectonics once we understood, how plate interactions occurred and things like that. But when we talk about a relatively new science, I mean, plate tectonics is just a little over 50 years old. It's not something we've known about since the 1800s. It's something that was even thought about in the middle of the previous century. So it is a relatively new theory. It's a still relatively new science, and we're still learning more as we get better tools to study how plates move and what the relationship of the plates to the inner structure of the Earth really is. So in this case, I want you to start paying a little bit of attention to India down here at kind of the bottom right, and you see China and the north and south China up to the top right. Over the next several slides, you're going to see these uh, uh, India start moving north, and we'll talk a little bit about the implications of the collision that occurs once we get towards the end of the slides. But this is Jurassic time, so the time of the dinosaurs. You can see the western U.S., there's a mountain range there, and then a coastal area. And as we move forward to the next step in the Cretaceous, you can see that whole area from Texas northward becomes an inland sea. This is when the Edwards limestone, Trinity, Glen Rose limestone, the highest point in Texas is limestone from this time period. El Capitan is a reef structure that formed in this inland sea in the Cretaceous time. And this is when we saw, a basically the motions that make our continent become what it is started during this time frame. So about 100 million years ago, you can see the mid-Atlantic ridge has generated between North America, Africa, Europe, South America. There's this ridge line running all the way down the length of the Atlantic Ocean that's responsible for spreading that open and making it into the ocean we see today. You can see India over here has detached from Africa and detached from Antarctica and is beginning to move northward. There's this large subduction zone along the southern edge of Eurasia. And as we move forward in time, we see India moving up and beginning to collide with the edge of that continental plate, if you will, is colliding with the Asian plate and starting to form the Himalayas. And in terms of North America, you can see we're pretty much in the shape we're going to be going forward as of 50 million years ago. There's not actually a lot going on. The Atlantic is still spreading. We still have a subduction zone that basically runs the entire length of Western North America all the way down through Proto-Central America and all of South America. But this subduction zone is really responsible for giving us Central America. As you can see, 50 million years ago, most of Central America didn't exist. There was not a continental mass that connected Mexico with South America, and it's been generated over time from the volcanism and subsequent erosion created by that subduction zone that's occurring. And that's the reason why we have, volcanoes in Mexico and Colombia and Chile and Peru and all of this. These are all related to this subduction zone that's also responsible for the Sierra Nevada and the Cascades up along North America. Okay, so moving forward to about 14 million years ago, you can see India is now fully collided into Asia, and it has generated what we now know as the Tibetan Plateau. And the fascinating thing about this whole collision process is that the all of what happened to all of that material that was on the surface between India and Asia. Well, the highest point on the earth, the top of Mount Everest and the top of all the mountains there, is marine limestones and shales. All the material that's now at the top of the highest points on the planet in that location used to be at the bottom of the ocean in between India and Asia. And so when we talk about tectonic collisions and tectonic forces creating topographic relief, that's what we're talking about. All of these mountain ranges that were formed and then eroded along the coast of western North America over time. That the Rockies are just the latest iteration of that. The Cascades and the Sierra Nevada are just the latest iteration. But we've had that same thing happening in the western U.S. or the western North America for millions and millions of years, and it's the erosion of that material from that topography that's created all the landforms around it. And the same thing with glacial movements coming down over time and back and forth from the north. It's taken a lot of that material that was part of that northern part of Laurentia and redistributed it southward into the southern portion of North America over time. Okay, so during the last ice age, what I want you to see here is how far down the sea levels went as of 18,000 years ago. If you look at the present day coastline, which is that white line of Texas there, you can see that the actual coastline 18,000 years ago was out at the edge of the continental shelf. Basically, water that's 200 feet deep now was the edge of the coastline. And keep in mind that every 20,000 years or 10 to 20,000 years or so, we go through a cycle like this where we have an ice age, it goes back, we have an ice age, it goes back. And so when we start looking at the landform along the Texas coast, I want you to think about the fact that, it was in its basically present condition approximately 50 million years ago or so. But for every 10 or 20,000 years, during that entire time, we've had an ice age that has raised the water level by 200 feet, lowered it by 200 feet. And so when you look at it modern day today, you can see the outline of where that former coastline was as the continental shelf. But our coast is, depending on where you are in Texas, can be 100 miles from that continental shelf inland. So just keep in mind when we start talking about coastal landforms that there's a lot of concern about climate change and things that may or may not bring about, several inches per year or several inches per decade of sea level change. But over the geologic time frame, we've seen hundreds of feet of sea level change that's shaped a lot of our landforms. So when we start talking about different, sea level changes, just bear in mind there's a difference in scale geologically versus what we talk about, being concerned about or not concerned about, depending on who you are over the next several decades. So, okay, so enough about this. I think we understand how the topography and the topography has been generated for us. Let's talk about what that means in Texas. So, the Geology of Texas map on the right-hand side here. This is the Bureau of Economic Geology's map. They generate this to kind of show you what geology would be exposed at the surface if you could get all that pesky soil out of the way. And on the left here is the ecological regions of Texas. And I think you can see there's obviously a relationship, at least in relationship to that band of material coming from northeast Texas down to the southwest there. And that's the Balcones Escarpment, essentially coming past Austin and San Antonio there. The difference between essentially the coastal plain and the Edwards Plateau and upland terrain. And then that pink spot right in the middle is the Llano uplift, where we had the volcanism that formed Enchanted Rock and a lot of the other granite mountaintops in the west of Austin and northwest of Austin there. And you can see those geologic landforms or geologic formations echoed in the ecological regions that formed around it. And what I'll say about that is that the soil that you develop or that you are capable of developing in an environment is directly related to the geology that it's forming from. If you have a marine shale that is entirely made of clay, you're not going to generate a loose, clean white sand from that. You're not going to get a sandy beach out of a marine clay shale. You're not going to get a a mudstone from erosion of a granite mountain like Enchanted Rock. That's going to form a rocky sand and eventually a grainy sand. But so the soil is dependent on the geology. But when you look as you go across Texas, there's another factor that comes into play, and that's the rainfall. So a lot of the places where we have relatively the same soil from one area to the next, or the same geologic material forming the core of the soil, it's affected by the fact that it either has more or less water available to it for chemical weathering, erosional processes, and things like that that develop the soil. So when you look at Texas rainfall, it's affected by the topography around us. We don't have, large mountain ranges in Texas, but directly to the southwest of Texas, down into Mexico, we have the Sierra Madre. And the rainfall in western Texas and even into the western hill country is almost entirely dependent on how much water makes it across from the Pacific in the form of the subtropical jet. And so when we have a strong El Nino and there's a strong subtropical jet coming through from the southwest, um, we can get more moisture over the top of the Sierra Madre, which is going to try to squeeze a lot of that water out as it's lifted from sea level. So we need a strong subtropical jet to come across to be able to get rainfall into western Texas and the western hill country. And if you look at the rainfall in San Antonio or west of San Antonio, you can see a clear relationship when you graph that rainfall against the El Nino Southern Oscillation Index in the Pacific. So it's a feature that's happening thousands and thousands of miles away in the Pacific, and combined with the topography to the south and west of Texas, is almost entirely responsible for how much rainfall we do or don't get in West Texas. And that amount of rainfall that we don't get out there is the reason why the soils in West and Southwest Texas are different than what they are in Northeast Texas, even though we have, when you look at that purple material to the far right hand edge of the soil order map, and then you look at the greenish and the bluish at the southwest, kind of down around Laredo and that area, that's relatively the same soil material to start with as far as geology. But it's the lack of rainfall that makes the difference in why the stuff to the south and west is different than what we get in the Northeast. So keep that in mind, that it's this combination of the topography, the geology, and the weather and other, moisture related things happening that are responsible for why, the different areas of Texas look the way they do. So it's all of those things, and I think you guys will learn all about all of it. But the geology forms the basis, and you can't, it's kind of a no go situation. If you don't have the right material, you're not going to get it, even if you apply the right weather and the right other factors to it. If you don't have the geology to start with, you're not going to get certain types of soils without it. Okay, so this is my slide on the hydrologic cycle. I understand you guys had a field trip or something to the Meadows Center. I like to think this isn't supposed to be any particular location, but I think it's a great uh, uh, facsimile of Central Texas. Where looking over to, if you're looking southward along the Balcones Escarpment, the right hand side is the Edwards Plateau. The left hand side is the beginning of the rolling hills and the coastal plain and that sort of thing going down towards Corpus and Houston and that area. And what I want you to see here is not necessarily uh, that, the specifics of any specific type of connection between rainfall and runoff and evaporation and infiltration and all that. But what I want you to see is that it's all connected, and it's connected on different scales, and it's connected on different cycles. But water that falls in the hill country is going to go into the Edwards Aquifer. It's going to go into the streams and springs and lakes in that area. It's going to feed the wells downhill down into San Antonio and New Braunfels and Seguin and all these places. And the water that runs off from there is going to infiltrate and go into the groundwater that's going down to Houston and College Station and places down towards the coast. And it happens at different scales. I mean, there's a good example from probably about early 2000s, I guess. They had a diesel spill at a cement plant that was on the Balcones Escarpment. They had a diesel release from a tank there, and it was about 8 miles from Comel Spring in New Braunfels, and it took about 2 weeks to go that 8 miles in the Edwards Aquifer. So they can have very, very fast underground transport in the right types of materials. In the case of the Edwards limestone, most of the transport that's happening there is happening in fractures and karst features that have developed in that limestone over time. I talked with a guy who was doing uh, a new type of scan, looking down boreholes in the Edwards Aquifer formations, looking for how the fractures formed, how they informed the flow, and that sort of thing. And he was getting some really screwy readings in one of the San Antonio water supply system wells. And finally, he dropped a camera down there to figure out what was happening, because his meter was just not getting good scans. He was getting all kinds of artifacts. And he dropped a camera down there because they had pulled the pumps out and the water was sitting still. And there was a fish swimming by his camera. It was a blind cave fish that had found his way through all the fractures and into one of the water supply wells and hadn't been sucked up in the pump yet. But it was causing havoc with his readings because it was sensing this fish swimming around his meter all the time. So just understand that there's fast transport like that, but on the same cycle, agricultural runoff from cotton growing or whatever up around College Station may make it down into the Chico Aquifer and wind up in wells in Houston, but that may take 1,600 years or 2,000 years for that water to get there. But it's going to get there. And it just depends, what you put into it, what you take out of it, and, what everything is related. And so, I'm sure everybody's heard now about the forever chemicals. That's going to be responsible for my retirement. Because we're working. That's the biggest problem that we're facing in the military bases and other places now is PFAS, perfluorinated chemicals, and those things don't degrade. They may degrade over thousands of years, but they don't degrade over 5 or 10 years like a lot of our other chemicals that I've spent most of my career trying to remediate. And so, as we have chemicals like this in our runoff and our wastes, we need to be even more careful than we ever have about where we put that material, how we treat it, how we protect our water sources, and things like that, because water is a very precious commodity and is getting even more so as we have droughts that have limited it for us.
Yeah,
So that's
we just had a question in the chat if we were running out of water, and I think you answered it just then.
Yeah, well, I mean, we're running out of fresh and easily accessible water. There are things we can do. My wife works for the Water Development Board, so I get kind of the skinny on a lot of this stuff. She's in the regional planning group, and one of the things that we're seeing a lot of areas look at is brackish water desalination. So, seawater desalination, starting with water that's 40,000 parts per trillion salt, is uh, it has a lot of issues. What do you do with the brine? Where do you put it? It's a complicated process, but we have a lot of groundwater that's not drinkable as it is. But if it may have 10,000 or 8,000 parts per trillion salt in it, and if you take that material and run it through a desal plant, you'll create a modestly saline brine, but it's not the same kind of really nasty stuff that's generated from seawater desal. And so there's things we can do to get more water, but it's not easy. And one of the things that's happening in the hill country right now, I'm sure everybody knows about Jacob's Well being run dry essentially by subdivision supplying water companies over pumping their permits. And that's a very real problem, is that we have easily accessible water up there, but we don't have enough. And if we keep building and we keep watering lawns and keep wanting to have golf courses and water parks and splash pads with every new subdivision, we're going to run those springs dry. And that, beyond just the kind of the ecological catastrophe of what happens when your spring fed river runs dry, there's also all those downstream water users that are using that spring, what eventually comes to that spring fed river. All those water users are suddenly without their water as well. And so I think, we really need, and my wife's tired of hearing me talk about this, but we really need to have a prioritization of uses that we uh, come to, where, I think if you look at it in Las Vegas and places like that, they don't allow non-functional turf. You can have the turf, you just can't water it, and it won't survive without being watered. So if it's a green esplanade in front of the subdivision, it's not watered. If you have, you know, a green lawn around your house is a thing of the past out there for the most part. So I think we're going to reach that point here where that's going to become a necessity, just because, there's so many people that want to come live here, and we need to be able to prioritize how we use the water so that we don't destroy some of the things that really have made, especially central and, the hill country what it is, with all the springs and spring fed rivers. So that's my soapbox on water. I'll try to stay off it, at least till you start asking more questions at the end of the talk. But um, okay, so just going to talk a little bit about alluvial processes here, and then we'll take our break. Um, so this is, if you think about a bayou in Houston, this top slide is, kind of normal water stage in a bayou in Houston. Um, when the water is moving, it has the speed of the water determines how much sediment can carry. Faster flow, more turbulent flow will allow water to carry more sediment and pick up larger and larger grain size sediment. So if you watch a flash flood out in West Texas or out in the desert Southwest, those flash floods, it's not at all uncommon to see the power of that water rolling giant boulders down the stream bed. Here in Houston, most of what we see is, clay and sand particles being picked up during floods. But what happens when we have a flood is that these bayou water levels raise up out of their banks. The water goes out over the side of the normal channel. And when it does, it runs into trees, it runs into subdivisions, it runs into downtown buildings, whatever is built, along the side of that. And as that all slows that water down, so that water flowing down the main channel carrying a very large load of various grain size sediment, when it goes over the banks in a natural scenario, it drops some of that sediment load because the water slows down. And over many, many years and many, many floods, we get natural levees, which, if you look down at the bottom, that's what it's showing, is basically a natural levee that occurs along the side of the bank. And then beyond that levee, there's this kind of broad plain of alluvial material. And that's what forms the really great agricultural land that we have among all our bayous and among all our rivers and along the Mississippi River and everywhere else where we have rivers that normally flood. We get that great agricultural soil because of all that repeated deposition and consistent replenishment caused by the floods. So we'll talk later during the case studies about what happens when we interrupt that natural process of building these levees and overbank deposits and resurfacing the terrain with soil from the flooding. So the other thing that we have around here is what are called river terraces or terrace plains. And if you look at the left-hand block here, you have a river channel flowing through a valley. You see that brown material is kind of all that overbank deposit that's built up over the time. And then along the edges where the flooding stops, you kind of get this, floodplain and then a bank where it's been slowly cut down over time by erosion and then redeveloped and redeposited within the floodplain. And if you think back to what I was talking about with the ice ages, during the ice ages, when there's a lot of glacier action, when there's a lot more snow closer to us and things like that, there were a lot larger volumes of water moving through our river systems. So the Brazos River, the Colorado River, the Sabine River, all the different rivers that are coming down to us from the north, all were fed by much larger loads of flow during past situations, past ice ages and interglacials and things like that. So what we see today often is this situation on the right where you have a historic floodplain that was much wider, and then you have a narrower floodplain and then a central channel. And a great place to see this, if you've ever ridden the MS-150 or if you know anybody who has, when you ride from Houston out towards Austin or out towards LaGrange, as you get onto 159 and 529 and 159 heading towards Belleville, you'll go across the Brazos River. But before you do, you go down a couple of these terraces. And then when you get to the other side of the river in a place called Burley, there's the moment of truth for every cyclist who didn't train for the MS-150, because there's a giant hill climbing back up one of these terraces. And then as you get closer to Belleville, you climb up a couple more. And you really find out who didn't do any training when they're the ones walking their bike up that hill. But it's the first hill you generally find coming out of Houston that really is tough to climb. And it's one of these river plain terraces that is on the Brazos River there. So it's a great place to see that kind of topography if you want to kind of just understand where it's coming, where our terrain in Houston and around us is coming from. Okay, and then the other thing, the other relationship that happens when we have moving sediment in a moving water channel is when it reaches a shoreline, whether it's coming into a lake or whether it's coming into a gulf or whether it's coming into an ocean somewhere. That water coming down the river, coming down the creek, coming down the bayou, hits a stationary water like the Galveston Bay or like the Gulf of Mexico or Gulf of America, whatever you want to call it. I've called it Gulf of Mexico for too long, so I apologize to anybody who cares if I do call it that. But what happens there is it drops that sediment, right? But it's not going to plug the channel forever. Eventually that water is going to build up and it has to find a way through. So it makes a series of these small distributary channels, they're called, where if it may run in these two northernmost channels for a little while, but then as it gets out towards the end, it's eventually going to deposit some sediment in that and block that channel and make it more advantageous for the water to easily flow down the middle channel until they get plugged up, and then they're going to flow down the south and they'll plug up, and then maybe it'll go back and go out the north. And over time, you build this wedge-shaped delta, this material out farther and farther from the coast until it becomes easier to go around the delta itself and start forming something. And you can see this along the Mississippi, where the Atchafalaya River is the natural next channel for the Mississippi. We've built the Mississippi Delta so large that the Mississippi would really love to go down the Atchafalaya Channel. But because of all the economic development we've created around the Mississippi River, we aren't letting it do that. We've got a river control structure there where I think we've let about 20% or 25% of the Mississippi River flow go through that control structure and down the Atchafalaya Channel. But if we didn't have that control structure there, a big chunk of the Mississippi River would want to go down the Atchafalaya River basin instead. It would flood out all the towns down along the way until we, rebuilt to the restructured river at that point. So John McPhee has a great book where he describes this whole thing, and his kind of parting shot on that is, I'm betting on the river, and I really am too. One of these days, we're going to have a conglomeration of events, and if we lose uh, that river control structure, it's going to make some of the scenes from Katrina look like child play, trying to get the river stopped and get it back where we want it. So I'm with John. I'm betting on the river in that situation. Okay. And then lastly, this is pertinent to how did the Texas coast and how did Galveston Island form, is when you get to the ends of these distributary channels coming through a delta, coming through a marsh that is forming at the convergence of a stream or a bayou or a river with the coastal water bodies. When you get this first flow, this fastest flow dropping out, it's going to drop out all of your large grain sediment, your sands, your gravels, things like that. And then as you get farther offshore and the water goes slower and slower, it's going to drop the fine sand and silt. And then farther out, it's going to drop the silts and clays. And when you get, far enough offshore that the current has lost all its motion and all of its impetus, you'll finally drop out those fine clays and muds. And this is how we get lagoons. This is these bars that form when you do it for long enough, and when you get wave action washing out more and more silt and leaving behind the sand, you eventually get barrier islands that form. And what I want you to understand from this is, think back to that distributary channel discussion we had in the Delta, where the channels are always changing, the water's always going different directions. Same thing with these bars. When the water level goes up, that bar is going to try to move inland. When the water level goes down, that bar is going to try to move out towards the ocean farther, because the water can go further with more energy farther out into the ocean. So when we talk about these, 100 and 200 foot high changes in water, sea level over time with these interglacials, these barrier islands along the Texas coast are dynamic systems. They are supposed to move. They're supposed to adjust to the water flow. They're supposed to adjust to the sea level. And what we've done, not just here in Texas, but all over the world, is everybody wants to live on a beach, right? We build on these barrier islands, but then because everybody's bought a piece of property and it has a defined line and it's theirs, they want to do everything they can to maintain what is theirs, which means anchoring that barrier island in place. And everything we'll talk about in the case studies talking about barrier islands comes about because we're trying to take what is a dynamic system that is meant to move and is meant to adjust and react, and we're trying to make it static and stationary. So keep that in mind as we go to the next phase of the talking here. So just a couple minutes to talk about soil. This is, as a geologist, this is my definition of soil. I want to see rocks. I want to see the building blocks of what's around me to kind of understand it all. So I've spent my entire career in the Texas coastal area drilling through soil, trying to get to, more cohesive materials that will tell me what's happening. But, I've made a great living mostly dealing with, what I would call soil, which is loose, unconsolidated material that may be, in the Texas coast, may be hundreds of feet thick. A geologist will call all of that soil, or, at very least, loose sediment, loose alluvium. It's not rock. It's not sandstone. It is, relatively unconsolidated material. The soil scientists are just a little bit more specific than that. That's the definition of a soil that you learn in the entry level soil science class at Texas A&M, and it is the first question on a pop quiz that Murray Milford used to give. And you're supposed to have memorized this from from the book and be able to write down the entire definition in the pop quiz. And I can tell you from experience that good rock gone bad is not an acceptable substitute for definition of the soil. So, but by this, what I mean, a soil scientist is looking at the top 60 inches. So when you go look at that Bureau of Economic Geology map of surface geology, you may be looking at a representation of materials that are 100 feet below ground surface, but that's the uppermost rock that you'll see in an area, or the uppermost formation. When you look at a soil science map, a NRCS or soil survey, you're going to be looking at a description of the upper 60 inches, the upper 5 feet, because that's all they care about. They're looking at the part that's agriculturally active, that is engineering for engineering purposes, that it's active for that. And so a soil scientist and a geologist are, they may use similar words. We may both call it soil, but we have a different definition and a different identity of what we're calling soil. So just keep that in mind when you're trying to learn geology. Don't go pick up a soil survey and think that that description of the top 60 inches is all you need to know. And when you're trying to learn soil, don't go look at the geology map and say, oh, this is what the soil is. So they're two different things. They're two different sources, and they're both useful for their own things, but just remember that they're different. Okay, lastly, how does geology affect us in a broad scale, right? Um, we have oil and gas production here because during one of those times, or in the Jurassic, when we had a shallow inland sea here, we had a very large evaporite salt, basically, where if you think about the Dead Sea type situation, where you have a very shallow sea, you have a lot of water coming into it and then evaporating out, leaving behind salt. We had a salt formation called the Luan Salt that was laid down. And as we've had millions of years of sediment, alluvial sediment deposited over the top of that, it basically, the salt is uh, basically, I'm trying to think of the right word. I can't think of the word. It's escaping me. Basically, it can move in reaction to having weight and having force put on over the top of it. And what happens is this salt in the Luan salt became buoyant relative to the layers of sediment around it, and you get these domes rising up and salt pillars that may rise up thousands and thousands of feet. And along the sides of those domes, where you have bedded sand and shales and other things, you create traps for oil and gas. And so a very large portion of the oil and gas development along the southeast Texas coast and offshore and over in Louisiana and all around the Gulf Coast is around salt domes. And now we're looking at before they couldn't do geophysics that would go below the salt. Now they've got it 3D seismic capabilities and better computer processing and things like that. And they're actually looking at subsalt formations, looking at deposits that are underneath the Luan salt and going after those for oil and gas development as well. So there's the presence of that salt, the presence of that sediment around it has created a large oil and gas capability for us here. And we also have the Strategic Petroleum Reserve being stored in salt domes, both in Louisiana and in Texas, where you basically, the salt is so strong, but also so dry, you can store liquids in it. You can create a cavern and pump oil into it and store it there, and it acts just like a storage tank. And so a big portion of our Strategic Petroleum Reserve is kept in salt domes over in Louisiana and Texas. As we talked about, those bayou and river delta and overbank flood deposits gave us great soil for agriculture. Our barrier islands protect our ports. The port of Houston came about because the great Galveston hurricane pointed out that our port wasn't all that protected, and so we the Allen brothers decided to build an inland port, and the barrier island protects that inland port. Same thing for Corpus Christi and other places along the coast. How does it affect us negatively? We get some subsidence and faulting. We have so much clay in our soils. We get uh, cracking of our foundations. There's two, people talk about there's two kinds of foundations in Houston, those that are cracked and those that are going to crack. And that's because of the soils that we have. We also, as all of that alluvial sediment that's been deposited slowly is trying to slide its way down towards the Gulf, it creates faulting. It's not tectonic faulting, but it's faulting that can change the relationship of structures built over the top of it. There's also faulting caused by the uplift of the salt domes that we just talked about. And then we also have subsidence because we've pumped so much groundwater and so much oil and gas out. We've got a great deal of subsidence in the Houston Galveston area that has caused its own set of problems. Like I said, I just talked about the shrink swell soils damaging our structures. The proximity of the Gulf is really positive for us. It increases our rainfall and humidity, which is great for agriculture. It's also not so great for if you really like, hairstyles and things like that. But it also buffers our temperature. So the difference between where I'm at now here in Bastrop and in Texas, the temperatures are actually quite different in the wintertime when we have cold fronts come through, because the warm water in the Gulf acts as a reservoir that buffers the temperatures down there and makes it harder to get that much colder down in Houston and Galveston and those areas. So it's protective of cold sensitive plants. And then the negative, like I said, the humidity, it also brings rainfall, brings hurricanes, brings flooding at times. So it gives and it takes. So how about a break?
Sounds good. We did have one question that I
Okay.
deferred to the end that was about hotspots and whether there's this idea that asteroid impacts may have helped create hotspots. Do you have any comment
I,
about that?
I don't know a lot of specifics about it. I think it's probably as good a theory as any. Obviously something has to create that weakness in the crust to allow the mantle to come up there. I don't know the specifics of any one location, whether they are or aren't, but I think it's a reasonable theory about how they could have formed.
Okay, great. All right. So
All
we
right,
want to take a 6-minute break and come back at 8:20.
sounds good. 8:20.
Sound good? 8:20?
Okay. Well, welcome back. I apologize if you hear any cats crying in the background. I've got a cat that's decided since I got up that it's time for her to be fed again. So the first case study we'll talk about is a topic we just mentioned right there at the end in one of the last slides, and that's ground subsidence and faulting in the Houston, Galveston Bay area. So I used to drive with my family every morning or about every other weekend to Beaumont. My grandmother lived over there, and my dad and his brother would take turns going over there every weekend. And so we got to drive through Baytown, right, go through what used to be the Baytown Tunnel, what's now the Fred Hartman Bridge, and drive past the Goose Creek area. And this was, as best I can tell, wasn't able to find a date for this, but I want to say it's around 1915, 1920, somewhere in there. This is the Goose Creek oil field along the edge of Galveston Bay, and you can see they were pretty exuberant in drilling oil wells and gathering a lot of there was a lot of shallow production from the area, so it was very easy to get a well. So they had all these wildcatters coming out here throwing wells in the ground. And when you look at 1970-ish, well, about the time we used to drive through, going to Beaumont all the time, it really didn't look all that different. There's a lot of these pump jacks that had replaced the oil wells or oil derricks. But there's still a lot of production out there. When you drove by the bay portion of this, it almost looked, as a kid, I almost thought you could almost jump from platform to platform without ever getting your feet wet. But there was a lot of development, a lot of production in this area, both oil and gas for these wells, but also the petrochemical facilities right nearby here also pulled an awful lot of groundwater out of the ground for uh, their processes in converting this oil and gas into chemicals. And so the Houston Galveston subsidence district created a map many years ago of subsidence from a 1906 survey to 2000. And looking, unfortunately, I don't have my cursor. I can't see my cursor for some reason, but the area right here where Galveston Bay meets Buffalo Bayou and the San Jacinto River there. That's the Ghost Creek oil field. You can see in that location there's been probably about 12 feet of subsidence. And that's the reason why the Brownwood subdivision that used to be there along the coast is now the Goose Creek Nature Center or Goose Creek Preserve, what I forget the exact name of it. But they had so much subsidence in that area that the subdivision that was built uh, earlier was no longer viable because of how often it got flooded. And so it got bought out, turned into a nature center. If you look a little further to the north and east of there, you see about a bullseye of about 9 feet. That's probably the Baytown, Exxon Baytown refinery. And then you go up along the ship channel there. You see a number of other facilities. There's DuPont and other, Roman Haas and all these other Shell and everybody else. And then that 7 foot contour right in by downtown Houston there in the center, that is most likely the central water plant for the city of Houston that used to pull a lot of groundwater there. And so all of these places along the ship channel were mostly from groundwater extraction that caused 10 feet of subsidence over 100 years. So the ground surface is 10 feet lower than it would have been had they not done that. If you look down almost to Galveston there, you see about 6 feet, and that's Texas City. Same situation down there. There was oil and gas production that was happening down there, but there was also groundwater being pulled out for the chemical plants down there as well. And so, how would Texas City in that area have fared in Hurricane Ike if they had been 6 feet higher? If you look at the mouth of Clear Creek there between the 5 and 6 contours on the western side of Galveston Bay, that's Kemah. How would Kemah have fared during Hurricane Ike if it had been 6 feet higher? So groundwater extraction and oil and gas extraction causing subsidence is a very real problem in Houston, and it's why the Houston Galveston Subsidence District exists. And the response has been to take almost all of our groundwater pumping for municipal and residential use and stop. Even as far out as you see the 7 out there at the northwest along 290, that's Jersey Village. And that even the areas out there are now mostly being fed by groundwater from Lake Houston surface water from Lake Houston or surface water from the Colorado and Brazos rivers. And so by taking away most of that groundwater extraction, we have slowed down the subsidence, and the subsidence from 2000 to now is probably measured in a matter of inches and not feet, but it's still happening, and it's a natural process. You see this kind of regional uh, you know thing centered around Houston. A lot of that's because of groundwater, but if you looked across the entire coast, you would see there's always going to be some subsidence just because we have a lot of loosely packed alluvial material that's sitting on top of very soft and very non-consolidated soil. So it's always going to be compacting. It's always going to be sinking a little bit. And the further you get to the coast, the more it's going to be sinking because that's the freshest and most recently deposited sediments. So that we'll talk a little bit about New Orleans later, but that's when you get over to New Orleans and that area, that's a much bigger problem over there than it is here because of some of the other factors it's causing. And this is one of my favorite parts of this topic. We do have faults in the Houston area. My dad worked for NASA in the late 60s and early 70s, training the astronauts in geology for the Apollo program. And one of the guys he worked with was a gentleman by the name of Yule Clanton. And when the Apollo program ended and NASA still had all these geologists on the payroll, they had a thing called Skylab and a thing, a couple of different a satellite called Landsat that they put up that took all these great images And guys like Yule were starting to look at all this data they had coming in and saying, okay, what can we do with this? And one of the things he noticed was that when you looked at Landsat data of the Houston area, you could see faulting. You could see there's a salt dome that's essentially in between Ellington and Hobby Airport here. This map is kind of skewed from how we normally see it, but it's basically the Gulf Freeway runs right down the middle of this map here. And there's a salt dome that's in the middle here, and all of these faults around this are all growth faults from that salt dome rising up in the middle and causing faulting around it. And like I said, it's not tectonic, it's not earthquakes, it's all soft soil and soft sediment layer faulting, but it does cause changes in elevation. And it used to be, before they did the most recent uh, expansion of the Gulf Freeway, when you drove down the Gulf Freeway right before you got to Dixie Farm Road, there was about a 1.5 foot jump in the pavement there. And that was this largest lateral fault going east to west across kind of between Maikawa Field and Ellington there. And you could see it, you could feel it, and they had to occasionally go out there and repave or restructure that bump because it was always growing by a few millimeters a year, a few inches a decade, and it still is today. But now they've put in some joints and things like that when they redid it, so that it's not as noticeable, and it will grow on its own a little bit without necessarily disrupting the freeway. But Yule went to the city fathers in Houston and said, hey, look, I've got this great data set. It shows us where all these faults are in the Houston area, and we can use it to make sure that we're not building critical infrastructure and that we're not building people's homes and subdivisions on top of all these faults. And I really think it'll be great for everybody to help keep us from making some mistakes. And the developers and the city fathers were so enamored with this data that Yule brought them, that the first thing they said was, shut up. Shut up. We don't want to see this. We don't want to hear about it. You're going to ruin our developments. We don't want to know about all this. Nobody needs to see this. And they went to his bosses at NASA and said, can you shut this guy up? And his bosses, were political creatures that were, their funding was driven by political processes. And so they came to Yule and very carefully explained, you need to shut up. Go find something else to do. Go find something else to focus on. And nobody did anything with these maps. They were basically left unused and unbenefited from for several decades, until 2006. Harris County Flood Control won a GIS contest by taking U.S. Department of Agriculture data and generating a map that won best overall in their competition. And the purpose of the map was to make the population of Harris County aware of geologic formations or active fault lines that will enable potential homeowners, real estate developers, business owners, blah, 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 to place their infrastructure safely. And this was such a popular topic that the very first thing you found when you clicked on this map was not the map. You found this data supplied by U.S. Department of Agriculture. Any questions regarding it should be directed to them. In other words, we drew this map, but don't call us asking why your house is built on a fault. We don't have any idea. This is just our map. We built the map. And it's such a great resource, and they're so proud of the fact that they won this that you can't find this map on their website anymore. So again, it's really not a popular topic, but still people persist. This is what the map looks like. You can see over to the, down to the south, you can see that set of maps along the Gulf Freeway that looks very much like what Yule made in the 1970s. If you look over to West Houston, you can see the Long Point Fault in that purple box. And if you go down go down Willcrest south from I-10, just before you get to Berry Knoll, there's about a 4-foot drop. It's been smoothed out when they repaved Willcrest recently and rebuilt that. But if you look off into particularly to the right as you're going south, you can see there's houses built right up along the edge of that fault, and there's a big drop in somebody's backyard. So it's it's a problem. And there's places all over Houston. The Eureka Heights Fault that goes right across the northwest portion of the loop there. You could drive down TC Jester and some of those streets around there and see buildings that have that fault running right through the middle of the building. And see, I used to have a picture in here of a laundromat that one side of the laundromat was about a foot lower than the other side because it was built across that fault. And so this is still an issue. And luckily, we have a gentleman by the name of Shubab Khan with U of H, who's now taken the latest iteration of satellite data, and his students have used LiDAR, which is a scanning tool from satellites that will basically take out all of the overlying structures and the trees and the grasses and everything that we built and just show us the ground surface. And so you can see that left-hand image, that kind of diagonal running across right through where it says pit, that's the Long Point Fault. And so that fault that we've known was there for how long? 50 years now. There's a stormwater retention structure built right over the top of that. There's buildings and houses and subdivisions built right over the top of the Long Point Fault where we knew where it was. We just built there anyways. So, these maps are available, I think, still on his, or at least you can find them from his website that I've got linked at the top here. But it's a useful tool, and it's something we should be taking more into account with our development, but we're not. Okay, so enough about that. So case study number 2, we're going to talk a little bit. We're going to go a little bit to the east and talk about the Mississippi River and one of the Katrina levee failures and how geology kind of played a role in that failure. So how the levees in the Mississippi River got developed, we talked about there already being kind of natural levees in place anytime you have flooding on an alluvial system like that. In and around New Orleans, they started in the 1700s building wheelbarrows. Using wheelbarrows, building levees, the really hard way. And they were required, any farmer who wanted to develop a farm along the river was required by state law to build their own levee to protect their land. And when we got to the late 1800s, the Mississippi River Commission was created because they started saying, hey, you know what? We've got all these floods happening, all these levees, and they're kind of this mishmash of different properties. And we really think we need this commission to, look at the lower Mississippi River and kind of, control how we work with levees to control these floods. And they started with what they called a levees only policy, and their goal was to create a self-cleansing river system. So basically contain the river within levees to the point where it was moving so fast that it never had a chance to slow down and would constantly scour out the channel of any sediment that tried to deposit. So we'll see whether that worked out for them here in a minute. But by 1913, that commission's control extended all the way up to Rock Island, Illinois. So they gradually over time kept saying, oh, well, we still need to move a little further north to get a little better control. We need to move a little more north. Eventually, they basically had control of the entire Mississippi River from Rock Island, Illinois, all the way southward, and have spent this, the time since then building more and more and bigger and better levees. John McPhee talks in his book, Control of Nature, about how, every time they'd have a flood along the Mississippi River, somebody would come along, a politician would come along in a horse-drawn wagon or on the back of a train or on a bus or a plane or a helicopter immediately after the flood and stand out amongst the crowd hoping for a change and tell them, we understand your suffering. This has been a terrible, unforeseeable natural disaster, and we are going to make sure that we build these levees bigger and better so that this never happens to you again. And you could see each time we had a flood, each time we had the politicians come through and promise something more, these levees got built up and up and up. And then eventually around New Orleans, we ran out of space to build the levees further out to the sides wider. So we built flood walls on top of that, where the roadway addition is shown here. We built a vertical flood wall with a sheet pile down into the levee to hold it in place and protect it. And so keep in mind what I was talking about around the coast and around New Orleans about if you don't let the river replenish the sediment, replenish the area around it, it is constantly subsiding, it's constantly sinking, and it's made worse if you're drawing water out. And so when you go to New Orleans, you now see that they've got these giant levees. They've built the river is not in fact self-scouring. It deposits its own sediment and then runs over the top of it. And so the river has been rising and been, basically built upward in between these levees, while the ground around it, deprived of the overbank deposits from the floods, has been sinking and not being replenished. And now you get the situation where New Orleans is, like 40 feet below the river level in parts of New Orleans, with only the levees keeping it from flooding. And so the other thing that happens is we've decided, instead of allowing these distributary channels to pick and choose where they want to go and kind of spread the deposition of sediment out over the course of the entire delta, we've picked one channel and said this will be the Mississippi River. This will be our channel, and we protected it with all these levees so it can't move. And what that has done is all these other abandoned deltas to the north and to the south that were large and thriving wetland marshes have slowly been eroded out by wave action. They've slowly been subsiding because they're not getting that constant replenishment of sediment. And the result is that Louisiana and the New Orleans area is losing the marshes and losing the estuaries that have protected it from storm surges and protected it from, wave action and large and damaging hurricane wave action. So while we've got this giant delta, the modern delta it's called on here, pushing the river and the river flow way out to sea, all that sediment that we would hope would have been deposited around the marshes and around the abandoned deltas is now being deposited out into the Gulf, and with it all the river pesticides and then all the nutrients that are being washed off of the cornfields in Iowa and everywhere else. And instead of replenishing places along the way through overbank deposits, they're now creating the Gulf of Mexico dead zone by over nutrifying the Gulf of Mexico. And so there's a lot of reasons why this was a bad plan. It had reasons. They didn't understand it well enough at the time, but we can see now with hindsight that building this kind of channel and not trying to fight the natural processes in doing so really has had a lot of negative and very serious consequences for New Orleans. So we'll talk a little bit about kind of that iconic, some of the iconic pictures we saw from Katrina, in a negative way. Iconic, I shouldn't say, not celebrating it. It was, horrifying for a lot of people. But this right up here where there's this blue and red star labeled 17th Street Canal Break at the upper left there, that's what we're going to talk about. And this is one of these levees that we talked about, where they have all these series of canals that run into New Orleans and run through to the river from Lake Pontchartrain. And on top of these levees, they had built flood walls. I want to say 10 or 12 feet high. And because they were trying to hold back more water, one of the things they had to do was look at what's the levee made of, what kind of soil is down there, to make sure that they weren't creating enough water pressure that they were going to force water through the levee and wash out the levee through weakness. And there goes the cat changing my slide for me. Okay, where's my mouse? Okay. All right. So I thought I went backward. There it is. Okay, so if you look to the right of where that canal break happened, the water depth got to 15 feet or more. So this area was at least 15 feet below the lake. So they had a lot of water already in the canals up there. And then when they had the storm surge come in, it got even worse. And I think most people who were alive and watching the news during Katrina remember seeing the Army Corps of Engineers trying to drop sandbags into this breach. But what most people don't realize when they look at this image is that you think this flood wall down to your right here toppled over backwards, and the pressure of the thing just toppled the wall and that's why it broke. That's not the case at all. When you actually look at the images, the flood wall is still intact and it's still upright, but the entire section of wall slid backwards. The entire levee slid backwards. And the reason for that is a very simple but devastating mistake in geology. When they went along and put these I-beam walls or these eye walls on the top of the levees, they also put this black line going down in the levee as a sheet piling, a metal piling that went the whole length of the levee. And what they were trying to do was cut off this marsh zone, this thing labeled marsh or marsh intermixing zone. And they were trying to cut that off because water can get into that and flow through to the other side of the levee. And so they knew that they were raising the water pressure enough by letting it go up onto that eye wall that they needed to be protective. And so they tasked a drilling company or two or five to drive down these walls and drill borings every certain distance. And at this B64 boring, somebody drew a log for that boring, and they wrote in this intermixing zone, this green layer there, they wrote gray clay CH, which is the layer below it, mixed with marsh layer intermixing zone. And somebody who was interpreting that geologic log back at headquarters, probably not a geologist, looked at that log and said, okay, starting here at 15 feet below water level, that's where we see CH. We can stop our piling 2 feet into that. But because they missed the part that said intermixed with marsh, they didn't realize that there was still weakness below the bottom of that sheet piling. And so when you look at this bottom image on this map, what happened is water went into that intermixing zone. The green layer went right under their sheet pile, went back up into that bottom into that brown marsh layer, essentially lubricated it, and the entire back section of the levee slid backwards like it was on a conveyor belt, 50 feet from where it was originally placed. And so, a simple mistake of misreading a geologic boring log was responsible for millions and millions and millions of dollars in damage, and unfortunately, dozens of lives lost in that flooding behind that wall. So, it may seem arcane, but it's important to understand what you're reading if you're going to try to act on geologic data when you're using somebody else's sources. So, okay, case study number 3. I call this Hurricane Harvey and the ever-flowing sands. We got a lot of questions right after Hurricane Harvey about why did we get so much sediment built up, and there was a lot of people blaming sand mining along the San Jacinto River and places like that, and that certainly, disturbance of the riverbed and disturbance of the floodplains around the river certainly played a part. But I wanted to highlight an example around downtown and in Buffalo Bayou Park that goes back to what we talked about with moving water, carrying a sediment load. And when you change the pace and the power of that water, you change how much sediment can carry. Right here in the middle of the map, you can see this pink watershed that is the White Oak Bayou watershed. And right below it to the south is the Buffalo Bayou watershed, reaching all the way out to the Addicks and Barker reservoirs. And then moving in towards downtown. When you get to downtown, those two bayous meet. Okay, and so coming in from the left here, you see Buffalo Bayou Park kind of in the middle left, and the bayou wraps around the north side of downtown through the theater district. And up along from the middle of the top of the map, you see White Oak Bayou coming in, and right where I-10 crosses White Oak Bayou, just to the south, those two bayous meet right there by UH downtown. And then look to the right of that, where the combined bayou goes to the right. What kind of space does that bayou have? Has nothing. There's basically a single channel. There's tall buildings built on either side of it. There's no place for an overbank flood to go. And so any water that comes into that location is going to have to go through that single channel, or it's going to have to go into parking garages and buildings and everything else. This is what White Oak Bayou looked like during Hurricane Harvey, looking straight down south towards downtown, almost to the top of the bank, almost over onto 45 and I-10 there. This is looking westward out from downtown across Buffalo Bayou. This is Buffalo Bayou Park in front of us, all this water trying to come from the west to downtown. When these two bayous came together at that point, there was only room for a little bit of water to go through there. And so it all backed up and slowed down into these parks. And what happens when water slows down? This is looking down into that same channel. There's no room for the water to go anywhere, right? Nothing but buildings. So this is what Buffalo Bayou Park looked like afterwards. All of that sediment that was being carried down the rushing Buffalo Bayou reached this point, slowed down, could no longer handle the load of sediment that it was carrying, and it dumped all of its sand all over the place in Buffalo Bayou Park. It's not sand mining, it's not anything else other than just bad flood design. You know, we have a channel that we're not allowing to have any space as it goes by downtown there to overflow and to flood elsewhere and drop that sediment somewhere else, so it drops it in the middle of our park. And now we have, this is where I feel bad for being a government contractor, because afterwards, one of the, if anybody was around and living in Houston during the time of Harvey, one of the big news stories was that Addicks Reservoir, which is this dark green area to the north and west there, and then Barker Reservoir, which is straight west, both of those were formed as flood channel or flood reservoirs to protect downtown from flooding along Buffalo Bayou. The whole idea was we had an important port generated by the Allen brothers. We had an important business center down here. We wanted to not have this huge wall of water come rushing into downtown if we had a flood. And so we built flood control reservoirs. But the Corps of Engineers only bought the land behind the property to account for their designed flood. They built these for a specific rainfall amount, and they built the levees to handle that certain amount of rainfall. But the levees were built taller because that's the way you build levees. You don't want the top of the levee to be exactly at the height of your design flood. So the levees are taller than that. And during Hurricane Harvey, we went well beyond the design flood. And we floated those things up to the very top of the levees, and we had water trying to run around the end of the levees over the emergency spillway. And the Corps of Engineers was faced with a really terrible choice. One was they were already flooding places behind the reservoir that they didn't own. So they had property, and they've since been sued for it and lost, that they have to pay for that property they flooded because they didn't own it, and it was their actions that flooded it. But if they wanted to release more water, Buffalo Bayou was already flooded. And so if they released more water out of the reservoirs than they already were, they were going to flood people downstream. But if they didn't release it and they had too much water flowing around the ends of the reservoir over the emergency spillways, they also risked eroding those spillways and having an uncontrolled release from the dam. So afterwards, the dam safety, and that's DAM, not DAMN, Department of Corps of Engineers, came to Houston and said, we want to redesign the Buffalo Bayou Channel to protect our ability to operate our dams. Basically, what they decided to do was, we want to do whatever we have to do to the Buffalo Bayou Channel so that in the case of another Hurricane Harvey, we can open our floodgates wide open without the fear of flooding people downstream. And so these reservoirs that were built specifically to protect downtown from flooding and protect the people along Buffalo Bayou from flooding, we're now going to redo the channel all the way from Barker Reservoir, this red line, and their project design area, as you notice, stops just before downtown, right at Buffalo Bayou Park, right at around Shepherd. And so the idea is we're going to redo Buffalo Bayou so that our flood reservoirs can release as much water as we want aimed right at downtown, but our project area isn't going to really include downtown, so we don't have to worry about what happens when it gets into downtown, right? And their idea of how to do that will look really familiar to anybody who's seen some of the other bayous in Houston and also seen the levee structures over in New Orleans. They wanted to take a approximately, I think it was like 210 feet wide lane, clear it out, slope it 1 to 4 feet, and put basically articulated concrete blocks all the way down the whole channel, all the way from Barker Reservoir all the way to around Shepherd. And so what does that do? Well, it doesn't account for the White Oak Bayou confluence because that's outside the project area, right? Doesn't leave any habitat for alligator snapping turtles, doesn't leave anywhere for sediment to deposit prior to reaching downtown. Really destroys the legacy of Terry Hershey. It's going to wipe out Terry Hershey Park. It's going to wipe out a lot of the riparian habitat in Memorial Park. And this was their plan, all to protect the dams that were built to protect downtown. So luckily there was a lot of uproar, a lot of people pushed back on this, and they pulled this design back and said, okay, we're listening. And they're still listening to the best of my knowledge, but this is something I think is, people concerned and who have seen history and know exactly what, how water works, we can see the outcome of this. This is not, I don't think, the best way to do this, in particular if we don't fix what's going on in downtown. All we're doing is setting up to cause a catastrophic flood and a huge sediment inundation of downtown. But it's going to be important for everybody who really cares about this to, be active and motivated to talk when they start accepting more comments on their next set of plans. And I understand there's people who were flooded in this, and that's certainly a concern. And I know they're going to have their own opinions on the fact that we do need to do something. But I think as hopefully from knowing the geologic history of other places that have tried similar things that don't work together with the way nature works, in terms of water and sediment movement, hopefully we can talk them into something more reasonable that's going to actually solve the problems and not just redeposit it down into downtown. Okay. Case study number 4, last one. So we talked about barrier islands. We talked about the fact they're dynamic systems. And this is one of the best examples of undeveloped, relatively undisturbed barrier island system functioning exactly as it should is the North Padre Island, the Padre Island National Seashore, 60 some miles of undeveloped dunes, protected dunes. And you can see looking at this is the sea level is actually very high here during this photo being taken, but there's a beach. And these dunes are 15 to 20, in some cases 25 feet high. Very tall dunes, entirely vegetated. The face of them gets occasionally eroded, but then you get all this seaweed that gets deposited from time to time. It locks in more sand, rebuilds a bit, revegetates. And over time, these dunes have redeveloped and they're consistently moving back and forth with the ocean. This is what it looks like when you stand on top of the dunes. You can see it's not just one line of dune, it's multiple walls and lines of these dunes stretching back off of the island. And it's all vegetated except where people have walked up here to take nice panoramic pictures of the dunes and trodden down the vegetation some. But for the most part, these dunes are all vegetated. And so this is what a natural barrier island that's being effective at protecting the bay behind it and protecting the land behind it looks like. So we go up further north up the coast to Galveston. This is looking down off of the end from a drone, I think, down off the end of the seawall, looking south down West Beach. And what do you see? Basically no dunes whatsoever. There's this small rise that they built in here. I know for many years people were down here throwing Christmas trees and things like that to try to help anchor the sand and create some dunes. and they were marginally effective in some places further down the coast. But for the most part, we've built so much infrastructure and so many structures and buildings up so close to the dune edge that we have no hope of creating a functioning and natural dune system that will be protective of what's behind it on the west side of Galveston Island. And this is what happens when you don't have a protective dune system in place anymore. This is where Bolivar Island, where basically houses were built all the way down to the edge of the beach. And when Hurricane Ike came through, it wiped the place clean, except for this one lone house that was built to a standard that would withstand just about anything. And so this is the outcome of not protecting, building infrastructure in places where they're not adequately protected and where you're not acknowledging the function of the natural systems that you're destroying when you put that infrastructure in place. And so, in response to Hurricane Ike and subsequent storms, we've come up with the Ike Dike. And what this consists of is all the way from High Island at the eastern end, all the way down to the entrance of West Bay, known as the project area, if you've been following along with Corps of Engineers terminology. They're looking at building a 12 and a 14-foot dune all the way along this entire stretch of the island. And then around Galveston, they're going to put a raised seawall by 4 feet and a whole series of flood walls and gates all the way around the island, and then a surge barrier across Galveston Bay. So, looking at what we know about New Orleans and what we know about the Mississippi River and what we know about natural systems, what's your first thoughts when you look at this? Well, first of all, okay, all this water during a hurricane that would be coming north and west onto the coast, where's that water going to go? We're putting up a bunch of dunes, so it's not going to necessarily be able to go over those dunes. It's not going to be able to go over the seawall. It's not going to be able to go through Galveston Bay. So it's going to go to the north or to the south, right? We're going to have these tremendous currents moving north and south along these dunes and along these walls. And this is their design. They've got a 12-foot dune out in front that's not going to be vegetated. They've got a 14-foot dune behind it that will be vegetated. And the entire purpose of that 12-foot dune is to be a sacrificial dune, basically be washed away by the waves. And when you think about, 80 something miles or so, I think is what the total distance was of coastline at a 12-foot high and a 14-foot high dune height, you're talking millions and millions and millions of cubic yards of sand that you're going to have to bring in. Number one, where's that sand going to come from? Number two, is it going to be contaminated from the bay or from the offshore areas where we're going to be producing it? And number three, where's it going to go when we have these tremendous longshore currents going north or south, probably south, based on the hurricane circulation that's trying to wash this sacrificial dune out? When you take several million cubic yards of sand and run it all the way down the coastline, what's it going to do when it gets down here to the south end where the end of the project area is at West Bay? We've got a bridge down there. We've got a channel coming out from where barges and things come out from Chocolate Bayou down there. We've got chemical plants. We've got the Strategic Petroleum Reserve a little further down the coast. What's going to happen to all those millions of cubic yards of sand that are a sacrificial dune designed to be washed away? And when we have to replenish it, how much is that going to cost? So I think there's some questions unanswered here that are, I'm a relative amateur coastal geologist. You guys are all, naturalists and ecology-minded people who can look at these things and look at what we've done in the past and realize that we're trying to fight very hard against a natural system instead of using the natural systems that nature has developed for us to be protective. So, the question is, how much of Galveston and how much of the west end of the island in particular could you buy for $23 billion? And, I think anybody who's ever dealt with a Corps of Engineers project knows it's not going to be $23 billion. It's going to be more than that. And so how much of that could we buy for that and go back to, the North Padre Island model of dune structures? I think there's a good question to be asked there. They've already approved all the funding for it, and I think it's going to go forward. But I don't think we're out of the point where we can still urge and ask and try to demand that this be built in a more uh, nature conscious way and responsibly relative to what we know the hazards are and know the problems are. But that's going to take a lot of action and a lot of voices being heard when they have comment periods on these things. So be ready to do your part if you feel the same way I do about it. And then the last part about this that I think really is dangerous to me is the elevated flood walls around Galveston. The idea is to basically circle the entire island within this colored block here with a flood wall and put a gate across off its bayou and put gates across any other channels coming in and out of it that can be closed in the event of a storm surge, so that what happened during Ike doesn't happen, which was a wraparound flood that didn't come over the seawall. It wrapped around the backside and flooded Galveston from the back. And you can see the depths of water on this map of, the ground elevation. If you have, what's going to flood if you have a 12-foot storm surge, it's going to flood everything up to this little yellow line here, which is basically all of Galveston. And all of anything behind the seawall is going to be flooded if it got in there. So we're going to depend on this wall. We're going to build it to a design storm, and if the storm comes that overtops it, what happens? Okay, we've got pumps. We had pumps in New Orleans. The pumps failed, didn't run. And people who were supposed to upkeep the levees spent the money on other things. And I don't think there's any reason to believe that, politicians in Galveston and elsewhere will do otherwise if they've given big piles of money to play with here. But the key to this that's really dangerous in my mind is that everybody who lives there is going to see this wall going up. Everybody who's thinking about buying property down there is going to see this wall and these dikes going up. And they're going to say, okay, cool, I'm safe. Okay, cool. If we've got a Cat 4 storm coming that's a 10-foot storm surge predicted, we've got a 14-foot flood wall around us. I don't have to worry, right? That's how people think, right? I'm protected. They just built this whole new system. I don't have to evacuate. I don't have to get out of here. And then what happens if this doesn't work? What happens if the pumps fail? What happens if the gate fails? What happens if we breach the top of the seawall with a higher than expected storm surge? Well, then you've got all these people back here who were safe, who didn't evacuate, and who are now trapped. And there's no way to get them out. There's no way to get to them. There's nowhere for them to go. And to me, that's a tragedy waiting to happen. And I think it's, we give people an artificial sense of security by putting these type of structures in here when that security maybe isn't there the way they thought it was. So just my thoughts on it. You guys follow along as the project starts to develop. And I think, hopefully we can encourage some more rational and logical things to do down here that maybe aren't as expensive, but maybe accomplish the same goals. And I'll leave you with a quote from Mark Twain talking about the Mississippi River Convention or River Commission. 10,000 river commissions cannot tame that lawless stream, cannot say to it, go here or go there and make it obey. And as John McPhee said, I'm betting on the river. So I feel the same way about the Gulf and Hurricane Ike and the Ike Dike project and all of that. So I'll leave you with that. And here's a few slides of outside resources you can look into just for, let me back that up. Geologic Atlas of Texas is great. The road map, the maps. There's also a series of books. They do them for every state: Roadside Geology of Texas, Roadside Geology of New Mexico, Colorado, whatever. If you really want to kind of learn what you're driving around, what you're seeing, it's a great way. It'll basically, you get the book, you open it up to whatever highway you're on, you look at the section where you're at, and it'll describe to you all the geology you're seeing along the way. So it's a cool way if you're like doing road trips, cool way to kind of learn the geology as you go. Um, Soil maps, a great place to get them. There's actually an online web soil survey, or you can go to your library. Usually we'll have the soil survey for your county if you want to learn more about what soil you have. And then for coastal planning, um, the Water Development Board has a great regional flood planning and state flood plan group. They are just starting the next planning cycle for the regional water planning, and I believe the flood planning as well. So it's a good time to get involved with your local. They do it by region, so they'll have regional groups. Buffalo Bayou Resiliency Study. This is the project page for doing the redo of the Buffalo Bayou channel, and I have not gone there real recently, so I don't know if they've updated it more recently, but I know they had pulled back that original design. A&M Galveston had a good website on the Ike Dike where they had this is where I pulled most of those figures from. I'm sure there's some updates the Corps of Engineers will be putting out as they go forward with studies as well. And then for philosophical reading, I mentioned it, Control of Nature by John McPhee is just a great book about places where man is trying to fight to control nature and maybe hasn't been successful in the past, and kind of some philosophical thoughts on how that goes. So with that, I'll leave it open for questions. I know I've gone just a little bit over, so if you guys need to get out, I understand. But if you want to ask questions, I'm glad to talk as long as you want. I can't hear you if you're talking. I think you're on mute.
Sorry. There's a question about the Ike Dike, or question slash comment. Wouldn't adding a 4-foot wall on top of the seawall block off a lot of the view of the Gulf from all the people frequenting the businesses on the seawall? Seems like their protection plan would end up actually hurting the economy.
Yeah, I mean, I think that's a good possibility. It's a lot of condos that are built with a sea view, and a lot of restaurants and things like that. So yes, I think there's a lot of questions to be asked and a lot of concerns that could be raised about all the different plans there. But that's certainly one of them.
And there was a question back about the Mississippi River and the levees. And is there anything that could actually be done now to?
Well, it's really there are places where they have learned their lesson and traded basically space for time in recent floods where they've had open farmland adjacent to sections of the river that are flooding. They've actually dynamited parts of the levees and let the river flow off into those areas. And what it does is it trades flooding, maybe a few farmhouses and a bunch of agricultural property for flooding a big city downstream. And so the people whose home got flooded, obviously it's not great for them, but it does replenish all their agricultural land with a fresh load of sediment. So there is a trade-off there, and I think you can do that along the river in places, but in like for instance in downtown where we've got that blockade, I really honestly think the only true answer there is probably something like what they've done with the Riverwalk in San Antonio, which is put a bypass tunnel or a bypass channel in, and that's going to take either condemning some property and building a channel or building a really large set of tunnels underground to do it. But that's really the only way to get all that water that's supposed to be on the west side of downtown to the east side of downtown without flooding downtown.
Yeah. There was one other comment about when you were talking about the subsidence map of Houston and because of the groundwater and the oil industry pulling the fluids out. The comment was, would the building of data centers aggravate the problem if they
Yeah.
start using large amounts of groundwater?
Well, if they're using groundwater, yes. In most cases in Houston, new users aren't going to be allowed to use groundwater. I mean, they're basically the Galveston Coastal Subsidence District functions as a groundwater conservation district that has a permitting process, and most of the time for any new large scale user, they're not going to allow a new well in places where there's already a subsidence problem. So they're going to direct them onto some sort of surface water. Now, the other side, and my wife would argue that this maybe is not the case, but one of the things, I was talking with somebody who does computer architecture, computer systems architecture, and that sort of thing. And one of the things he pointed out was that data centers use a great deal of water right now because they have to cool off all their systems, because their systems are using a lot of electricity. The electricity that they use is their single largest expense. And so there's a huge incentive for them to reduce the amount of electricity they use by adapting the architecture, changing the different systems, and making enhancements with their data centers. So over time, it's likely that as that energy usage goes down to use to store the same amount of data and process it, the water usage to cool that electrical usage will also go down. So there's probably likely to be a very large impact initially, but it's also likely that over time that impact may go down as they get more efficient in their power usage. And also, frankly, a lot of there's a big boom to build these things, but a lot of them aren't going to ultimately be economically successful. So not all of them will be functional, 10 or 15 years from now, most likely. So I do see a question there about fracking.
Yeah, I was gonna.
Um,
Yeah.
the problem with fracking is really in my opinion at least, is limited to the fact that there's bad frac jobs. Sometimes people have blowouts in their wells. They do use very large amount of pressure to do the fracking, and if you're doing it in a shallower unit, or if you're not properly cased, you don't have the well properly cased and cemented in, that's when you see cases where somebody went in and fracked and blew out their well and put oil into somebody's water well or something like that. Usually the places they're fracking are 10,000 feet down, and that is not going to impact somebody's water well at 500 feet unless they blow out their well, unless they somehow propagate a fracture upward through 10,000 feet of material. So it's really the shallow locations, and it's the improperly done ones. But I think the Texas at least has a really good underground injection control group that does a great job reviewing fracking permits, or reviewing any type of injection permits. We have to do it when we're doing injections for groundwater remediation. We have to go through them as well. So I think they do a good job, but it's really going to be more about making sure that companies that don't do a good job and that do have blowouts and do have problems with their fracking jobs, that they're properly held accountable for them. And in most cases, they won't survive financially if they do it too often. So, that's really the key to me, is to hold those groups accountable for it. And then the other side of it is the disposal of the brine water from the fracking. I'm sure everybody, if you ever look at the USGS earthquakes page, you see Oklahoma and West Texas now have all kinds of earthquakes showing up that we didn't used to have. And most of that is because we're injecting so much brine water, we're reactivating old, fractures and fault patterns out there. And I think if you do too much of that in seismically active areas, you do run the risk of creating an earthquake that may be larger than you would want. But hopefully we control that and distribute that injection more so in the future, so that we're not creating a hazardous situation with that.
All right. Well, we appreciate it very much. You can look in the chat and you can see that everybody loved it, as they always
Yep.
especially love the case studies, which are incredibly interesting. And
Yeah, feel free to distribute my email as well if anybody has questions they want to ask later or anything like
yeah,
that.
and I was just going to tell, somebody was asking about the links. I took some snapshots of your slides with the
I
links.
can send you a PDF of this if you want,
Sure,
so you can distribute it. So
that would be fantastic. Yeah,
yeah,
that'd
no
be
problem.
great. Okay.
All right.
And other than that, I'm going to let everybody go. I just want to remind you, VMS, you can put in 2 hours and 15 minutes for this, since we ran over a little bit. And our next class is on Thursday at 7. I will send the link out again tomorrow, and we'll defer the rest of our minute of opportunity and all that. We'll do that on Thursday. So you'll have a double minute of opportunity on Thursday. So thank you, everybody that attended. And thank you, Bill, again.
All right.
And everybody have a good evening. See you.